Today, I'd like to introduce to you the genetic algorithm framework developed by myself using Python, called pyrimidine. I've already uploaded to pypi, and you can install the package using the install command. As a beginner, you can use this import statement to import the functions and classes in pyrimidine. Let's take a look at a simple example, the knapsack problem. The knapsack problem is a classical optimization problem. Many intelligent algorithms are tested using this problem. The solution to the knapsack problem itself is a binary sequence, making it an excellent candidate for testing genetic algorithms. Now, I will demonstrate how to use the pyrimidine to solve the knapsack problem. First, import the class that will be used from the pyrimidine package. I will explain the classes. The problem is already defined in this model. I won't redefine it here, but users can define it by themselves. What you need to do is define an objective function. In this problem, the function maps a binary sequence to a real number, that is fitness. Here I just set the number of bags to be 50. This class method will generate a special problem randomly. That is, set the parameters wi, ci randomly. In fact, this variable is an object of this class that is defined call method, so it behaves like a function. Here we directly use binary chromosome class to construct the chromosome as binary sequence, and let its length to be the number of bags, n bags. Next, we define individual class based on the chromosome. An individual is defined as a container of chromosome. The so-called container is like an algebraic system, not necessarily defined with operations. Here, it is recommended to inherit mono individual, forcing individuals to contain only one chromosome. The solution of the problem is just a single sequence of 1 and 0s. This is the code. You should set element class to be binary chromosome. If you didn't set the default size previously, you should set it here. You needn't to set the size of the individual, which is the number of chromosomes, because the number must be 1. This fitness method is very important. You have to define it to compute fitness. The method starts with underline. It's usually the most basic operation to do the dirty work. In fact, each individual has a fitness attribute that is essentially a wrapper for the method. We also have a very concise equivalent writing style. This style imitates the format in Python's standard library typing. This code represents this part, and this code represents this part. Using setFitness, we can avoid the class syntax. Now, we define population class based on the individual. The population is regarded as a container of individuals. So the form of definition is the same as that of the individual. Here we inherit standard population and set the two parameter as the individual. I believe everyone is aware of its equivalent style like this. In fact, the two classes, individual and population, are implemented using a container meta class. The concrete implementation of meta classes will not be covered in this video. Algebraically, an individual with only one chromosome is equivalent to a single chromosome. So we can also define the individual as a chromosome. Here we should set the default size. It's not the number of chromosomes in the individual, it's the length of the chromosome. Here we define the thickness, and we needn't to define it like this. We needn't use the decode. This method is to translate the individual to the solution because it's not the solution itself. But this individual represents a solution directly. We can write it in one line like this. It's very concise. Of course, we can define the population as a container of chromosomes. It is totally legal. And the whole population can be defined in one line like this. You can see there is a small trick here. Move the set thickness outside of the brace because the set thickness is defined for the chromosome as the individual of the population. But the effect is the same. So I just move it out of the brace and make the code more concise. Finally, we use the class method random to generate a special population randomly. Of course, you can use other methods to initialize a population. Then we execute the evolve method. You can get the best individual attribute, that is the individual with maximum fitness. Use solution to get the decoding form of the individual, that is the solution of the original problem. To achieve visualization, we should set history to true. This will return basic information about each generation of population. The result will be encapsulated in the data structure, data frame of panels. You can use the APIs of panels to handle with the data. For example, plotting the fitness evolution curve. You can see the result, evolutionary result. You can see the evolutionary result from the picture. Finally, let me explain the basic principle of the design. The core concept is the container. It is understood as an algebra system. I use the expression to denote a container. S equals to A in type A, and S itself is in type S. Equivalently, it can be expressed as S in type S A. It really looks like an algebra system. I call it such design algebra-inspired programming. As definition, a population is a container of individuals. So a population equals to individual in individual type in population type. Equivalently, we can denote it as population individual. It is very easy to define multi-population. A multi-population is a container of population. So we denote it as, and equivalently it can be written as. Okay, I complete the introduction of pyrimidine. I hope this package help you solve optimization problems in various domains using genetic algorithms. Finally, I remind everyone to download it from PYPI. It is also hosted on GitHub, so you can also download it from GitHub. Thank you for watching the video.